All right, guys. So just want to get you set up with enzymes. And we already talked a little bit about enzymes. We talked about how they are organic catalysts. The term organic meaning that they have both carbon and hydrogen. They're organic molecules. They're actually proteins. And catalysts meaning that they carry out reactions without changing themselves. We talked about and you modeled that enzyme looks like a complicated molecule, which we can simplify by drawing kind of a blob. And the thing that it acts on is called a substrate. And where those two meet is called the active site. And the active site is like specific to the substrate. So it always fits kind of like a lock and a key. So this results in certain enzymes acting on specific substrates. So that concept is specificity. So for example, this enzyme will act on the two circular substrates because they fit to that enzyme. Whereas this enzyme here would act on these rectangular substrates because its active site is specific to those substrates. So we talked about when you modeled how the enzyme will join with the substrates, and that forms this enzyme substrate complex, and they all kind of meet here at the active site. We talked about how they enzymes can carry out two processes. One of them is dehydration synthesis, and the other one is hydrolysis. And dehydration synthesis is when it builds things, such as in a ribosome, builds larger molecules by removing water. And hydrolysis is where enzymes break down molecules by adding water, like what would occur in your intestines. Now we want to look at some different factors that affect enzyme activity. So the first thing we'll look at is temperature. And on the x-axis of this graph, you see temperature. And on the y-axis, you see the rate of enzyme reaction. And what you see is that the enzyme is inactive at very low temperatures. And as temperature rises, the enzyme activity will steadily increase until it reaches a peak activity, and that's called the enzyme's optimum temperature. So in this case, it's around 41 or 42 degrees Celsius. And then what happens to enzymes is as they continue to heat, their structure rapidly changes shape and they become denatured. So this enzyme would denature at around 46 degrees Celsius. And once enzymes are denatured, that's it. They can no longer be used. And the reason for this is if we look back here at what enzymes actually look like as these really complicated protein molecules, when these protein molecules are heated up, energy is added to them. The individual atoms tend to vibrate. And what happens is bonds are broken and the enzyme will just completely change shape. Imagine the touch me not flower. And when you touch it, it just kind of explodes. And I don't know if it's that dramatic, but the enzyme will permanently change shape. And its active site will no longer fit its substrate, so it just no longer works. The cold effect is also a result of temperature. So as the temperature increases, the enzyme comes into this perfect shape with a really nice active site. And then if it increases too much, the shape changes dramatically and the active site no longer functions. So that's how temperature affects it. Another thing that affects enzyme activity is pH. pH is a measure of how acidic or basic something is. That's really oversimplified way of describing it, but it works for our purposes. So acidic means that there's maybe a better way of saying it is that neutral is kind of like water. So it's not super reactive. It dissolves things, but it's not super reactive. It doesn't want to tear molecules apart. If you get very acidic, you wind up with a very reactive substance that wants to tear other molecules apart. And if you wind up with a really basic pH, you also wind up with a very reactive substance. So strong acids are reactive, strong bases are reactive, and then in the neutral you have water. Notice, importantly, that acids are lower on the pH scale and bases are higher on the pH scale, with neutral being 7. If you look at the bottom here, you can just see some different examples of acids, like lemon juice and battery acid are very acidic, whereas soap and ammonia are rather basic. So how does this affect acid enzyme activity. Well, here's a graph that shows the enzyme activity of 3 enzymes that are active in the human digestive system. And here's a pH scale on the x-axis with acidic down here and basic up here. Here's our enzyme activity graph. And so here you can see that pepsin, which is the enzyme found in your stomach, is very, very acidic at its optimum pH. So pepsin works great at a pH of 2. And then when the pH gets higher, pepsin doesn't work so good. It's around 5, it just doesn't work at all. Here's the enzyme found in your saliva and your mouth. Your mouth's pH is 7. And so the the enzyme salivary amylase works best in your mouth at that neutral pH. And then here's another enzyme called arginase that breaks down amino acids in your small intestine. Your small intestine's pH is basic. Small intestine actually has a pH around 9.5. So arginase works best in the small intestine. In your stomach, it wouldn't work at all. So here you see these enzymes have optimum pHs that they function at. And here you see the enzymes have optimum temperatures that they function at. How much substrate is available can also affect enzyme activity. So here on the x-axis of this graph, you see substrate concentration. And on the y-axis, you see the reaction rate. So here you can see you have enzymes hanging out with nothing to do. So there's plenty of enzymes, not enough substrate. So not a lot of chemical reactions are taking place. But as you add more substrate, you can see the red line on the graph here. As you add more substrate, more and more enzymes have jobs to do. And so the reaction is going to speed up. But eventually you are going to reach a point where you have too much substrate. And so the enzymes working as fast as they can still can't get to all the substrate that's available. So what happens is the graph plateaus. You can't work any faster than that because you don't have enough enzymes or workers to carry out reactions. So this would be like the optimum substrate concentration right here. It's where you've reached your peak enzyme activity without having too much substrate. And this final graph shows enzyme concentration versus the rate of reaction. And so here you see a similar thing, okay? So down in this end of the graph, let's assume that we have plenty of substrate, plenty of molecules for the enzyme to act on. But on this lower end of the graph, you only have 1 or 2 enzymes. So not a lot of work is getting done. And as you increase the number of enzymes available, more and more work gets done, more and more chemical reactions are taking place until eventually you have too many enzymes. So there's more enzymes than substrate that can be reacted on. And so you have enzymes that are just hanging around doing absolutely nothing. So at this point, you're just wasting extra enzymes. So right here would be your optimum enzyme concentration because you have enough enzymes to do the work as fast as possible, but not too many enzymes. Okay, so that wraps it up for that. I think that you probably will want to do some practice questions on enzymes and what affects their rates of reactivity.